You might have observed that the second unit p-n junction is quite small and have very less topics. That's why questions based entirely on p-n junction are having less chances to appear in numericals based examination. However, the concepts of p-n junction are sometimes combined with the topics which you will study in this unit. Like, one of the common optical device is photodiode. You see, it is actually a type of diode. Not only this, formulas for other optical devices also comes from basic topics of the p-n junction. Topics from first 3 units can be merged together to make tricky questions. Keep your mind broad open so that you can connect different topics of different units. Our first topic in this unit is optical absorption. We have mainly 3 types in which electron hole pairs can be generated. First is thermal generation. Second is impact ionization, which we have also studied when we were discussing about avalanche breakdown. And the third is optical generation. In the first unit, we were talking about generation rate, but that generation rate was caused due to thermal agitation only. In this unit, we will be focusing on generation rate, which is caused due to the photon bombardment. Now suppose that we have energy band diagram like this, with EC and EB as the minima of conduction band energy and maxima of valence band energy, and EG represent the band gap energy. Now, for a photon to excite an electron present in valence band to make transition to conduction band, the maximum permissible wavelength for the photon is equal to Planck's constant h into speed of light c divided by band gap energy Eg. And if the band gap energy is provided in electron volt, then we will be getting the direct value of wavelength in micrometer. If the wavelength of the photon is less than maximum wavelength, then upon striking an electron, a photon can generate an electron hole pair. If the wavelength is more than the maximum wavelength, then the corresponding energy will be insufficient for making an electronic transition. But it does not mean that if the wavelength is lesser than the maximum wavelength, then all the photons will definitely result in electron hole pair. It is not possible for all the photons to create electron hole pair, as some of the photons may interact with semiconductor lattice, whereby the photon energy will be released into the crystal lattice in the form of heat. Some of the photon may interact with dopant atoms, which is also an unwanted interaction. We are concerned about only those photon interactions which takes place with valence electrons of the semiconductor generating electron hole pairs. And for the same purpose, one parameter known as efficiency factor is defined, whose value lies between 0 to 1. 1 being the ideal value, meaning that every photon results in electron hole pair. Now assume that we have 2 semiconductor blocks and we are intentionally releasing photons so that it strikes on the front surface of the semiconductor. You can see that even if total number of photons striking on the whole surface are same, but still the concentration will be different, as the surface area on which the photons are striking are different. So another term which will be used commonly is photon flux intensity, which is expressed in terms of energy per centimeter square per second. As the name defines, photon flux intensity specifies the intensity with which photons are incident on the surface, and intensity of photons is calculated as energy of photons striking per unit surface area per second. Now suppose we have a semiconductor block like this, and we mark intensity at any 2 random points, say one at the surface and other inside the semiconductor. If we talk about a realistic case, then obviously the intensity IV1 is greater than IV2, as we go deeper inside the semiconductor, more and more number of photons are absorbed by the semiconductor, leaving behind decreased number of photons, thereby decreasing intensity.